So let's carry on where I was earlier. So I wanted to give you this theorem, which is that ACDF PQ, or suitable combinations of PQs, is complete, and that this is in fact, the exact family of completions of ACDF. It's pretty clear that I mean, if these are all complete, then you can't get any other completions because I already explained how characteristics work. You know, ring morphisms behave nicely with characteristics. Okay, so really our goal is to prove this theorem, and I just want to give you a very quick sketch proof for the equal characteristic case. Note I am including equal characteristic P. So, Francie's already given us some nice tests for QE, and there's a very close test for very morally close test for completeness, and hopefully this should look a little familiar. Take K and L, two models, and I'm writing them without being explicit about what all the other symbols should be called. So these are L val structures, and these are models of the theory ACDF, let's say PP, but I'm allowing P to be 0. It'll be fixed from now on. So I'm taking two models, and what we want, what I want to show is that they're elementarily equivalent, and it suffices to prove the following. That K star there exists. How about I write it like this? That one model embeds into some elementary extension of our given model L some L star over suitable base, which could be, if I want to state it like this, it better be somehow, this better be an embedding argument over any suitable base, and in particular, if I can do it over models, that's fine. So, what does that mean? That means I take two models with a common submodel, and I need to embed one into some sort of big enough version of this one. All right? And now, yet another way of saying it is I'm allowed to assume this is countable, I'm allowed to assume this is an arbitrary countable extension that is also a model. I mean, these should both be models of our given theory. This should be some other model extending this one. But now I suppose it's as large as I like. I should be able to embed this into this, over this. All right, that's the game. That's a very similar game to the elimination of quantifiers criterion that Francie gave us earlier. And that's because these are very close properties in some way. So how do we do this? So it suffices to prove that. So now we do the following. Model theoretic magic means that I can suppose that I'm given embeddings of the value groups and residue field already. Right? I may assume that because essentially we already know we already know what the theories are on the value group and on the residue field, namely the group of an algebraically closed valued field will always be a non-trivial divisible OAG, ordered abelian group. And there's only one theory of those. That's already a complete theory. Residue field of an algebraically closed valued field is itself an algebraically closed field, right, of the same characteristic that we started with, and there's only one theory of those. So basically we already have our goal for our theory of value group and residue field. Okay, so the goal is already true in those sort of smaller associated substructures. And now what we do is inside K, let's look inside K, what do we have? I can take a maximal extension actually, let me argue this over the prime field actually at the moment. That's slightly easier. I want to just argue something over the prime field. Take a maximal trivially valued subfield. Little k. Maximal trivially valued subfield. And such a thing always exists. That's a basic Zorn argument. What about this? Is these are ordered abelian groups here. They're additive. We write them additively. But what are they doing in the field? That's coming from multiplication. So if there was a section of the valuation map, it would appear as a multiplicative subgroup on which the valuation was an isomorphism. And I'll justify this a little bit more carefully later, but in this ACVF setting, such things always exist. So there's a kind of multiplicative copy of the value group. So since I write this group as additive, I want to write this as a kind of token multiplicative version of that. Such a thing always exists inside an algebraically closed valued field, essentially because you can always take roots of things. So start lifting elements, and then all you have to do is take roots. I'll say more about that. So we've broken our valued field, our algebraically closed valued field, into a maximal trivially valued subfield, which will actually also be an algebraically closed valued field. Sorry, an algebraically closed field with a trivial valuation. We've got this thing here, and if I take all these elements and then generate a field with them, I get something like that. These things are what Victor calls valuation disjoint. And in any case, certainly as fields, they're linearly disjoint, so we can take the tensor product, we can amalgamate them, and we get a subfield on which the valuation already has residue field little k, already has value group all of little gamma, big gamma I mean. So that tells us that this extension, what's left, there's no new elements in the value group, no new elements in the residue field. That's called immediate. So that's now an immediate extension, which is to say that the value group and the residue field don't change in this extension. So the only thing left for us to understand, if you want to see this as a kind of structural argument, is what this extension looks like. Yeah.
So K is the maximal subfield. So is it true that K is just equal to the elements with valuation 0?
It will be some elements of valuation 0, plus 0, which has valuation infinity, but
Okay.
there's not just one of it in general. There's lots of copies of such a thing.
But if you even have one element in there with a non-zero valuation, then it would not be trivial anymore?
If there's an element there with non-zero, non-infinite valuation, then it's not trivially valued. So the question remains,
how do you know that that maximum for the revalued field has the same, how do you know that field is actually the same as the residue field?
So, yeah, I mean, I guess you can agree that it's, I mean, that's essentially the checking the maximality, right? If you look at the residue map restricted to such a thing, that has to now be an embedding of rings.
Yeah.
So the only problem is if there's something in the residue field we haven't hit yet. If there's something transcendental, you can lift that arbitrarily. If there's something algebraic, if it's separably algebraic, you can lift it with Hensel's lemma, or just in this case, we're in an algebraically closed setting, just choose the lift, choose a lift. And everything's perfect, so there's no issue with inseparability because everything can be closed under p-throughs.
Okay.
So the question that remains is, what about single elements? Let's just start with one element at a time. Of K viewed over its subfield What about that? Well, up to isomorphism, they are described by their, what I would call their linear type. Has a lot of names. Let me write down what I mean by it first. So let's take an element, single element A. There, it's determined by the set of inequalities of this shape. Vx minus A is greater than gamma for various, for x in this and gamma in gamma. And this is just a set of, a set of data. It's nothing more than a partial type in the model theoretic sense. That just means a consistent collection of formulas. So it's a consistent collection of formulas. And it was first studied, this kind of thing, at least to my understanding, was first studied by Kuhlmann or Ostrovsky. Anyway, the very serious paper that I would like to push you towards is by Kuhlmann. And he proved that this information is enough to determine the isomorphism type of the rational function field as a valued subfield of big K over this valued subfield. And why is that? That's because how should I put this? Essentially because this thing essentially because sorry, let me write it like this. Essentially because values of polynomials element A, where f is a polynomial over here, with one new variable, are determined by their limiting value in this field. I should give that a name, shouldn't I? Let's call it f. So they're determined by their limiting value in f as x sort of tends towards a, meaning as these well, I'm going to write this out a little bit more precisely in just a second, so I don't want to get too bogged down in that. Yes, Leo.
So I'm not sure you said this, but you also need the algebraic type of A, right?
Well, I don't. I think because I've already. Well, I guess I'm saying that.
Are you saying A is transcendental?
I guess I'm looking at transcendental ones. Yes. So single element A of A viewed. I should have written that. Let me just write that down. Thank you. Okay. The point being the following. Let me draw a little picture. So these inequalities, if you view this as your fixed element in capital K, and if you imagine now x can run through any element of any valued field extension, what does this define? It defines some kind of ball like that. Now it might well, but I should say it defines, the inside part. And yes, it's open, but that's not a big deal. Now, it might be that if you allow this thing to vary only through f, it might be that the values you get never get beyond some sort of radius here. You can never get closer than some sort of cut in the value group. That could, in principle, be a problem, but what the magic of algebraically closed valued fields, and more generally, in a second we'll see in the Henselian equal characteristic zero, and then more generally the Kaplanskian setting, is that the limiting value of any polynomial along such a path exists, is meaningful, it tends to some sort of, it's eventually constant. We don't need to sort of worry about the fact that that f doesn't see exactly what's going on inside this ball. In fact, as far as f's concerned, if you start off with a polynomial f like that, and then take x, getting closer and closer to a through f, at some point it will find a limiting value, and it's that value that f of little a is taking in big K. So this is saying that this data is already enough to fix the values of elements in the field extension generated by this singleton. And that's the rough idea. And let me now just continue with the argument phrase in f, and then I'll go back into this line of thinking. So this...
Can I ask a question? I'm also confused. Suppose you had an element B inside that bit, very close to A.
Yeah.
That was an algebraic. That was an algebraic over the field K tensor. FP.
You couldn't get that actually in this case.
So it's not possible.
No.
Okay. So
I'll
yeah, because if you did that, then you wouldn't be able to detect just from linear type.
Exactly.
What the value of the minimal.
Exactly. So in such a setting, the linear type does not tell you everything.
Okay, but you're saying it doesn't happen.
In this case, where you already have an algebraically closed field here and a in this case, even divisible value group here? No, it doesn't occur.
Okay.
I should say that these kinds of things are called, or more or less, this technology is called pseudo-Cauchy sequences or pseudo-convergent sequences by Fransky and other people. And there's the notion of approximation type by Franz Victor Kuhlmann, which is a very similar batch of ideas.
And just to make sure, when you write down FP to the gamma, you're just talking about the field generated by those things. You're not taking any series.
No series at this point. Exactly. No series at this point. So let's now come back to the setting in which we've got two fields. We've already got some embeddings of value group and residue field, and using those, we can push this sort of tensory bit on the left to an analogous tensory bit on the right. A bit ambitious with that line, wasn't I? Right, so because this is just some sort of straightforward tensor product, we already have, by hypothesis, some sort of map going from KV to LV, some sort of map going from VK to VL. So this part's just straightforward now. So there really is a embedding of valued fields like that. And now what we're doing is we're asking, and what about the rest? What about extra elements here? Extra elements A? Well, that's a good question. But if we take, firstly we should take the Henselization here. And now it will be the case, and this is the thing that I'm slightly skipping over but I will come back to, this will now be in the case where this sort of linear type already tells everything we need to know about A. And so now let's look at what does it tell us. Well, it's a bunch of information like which balls with center something in F and radius something in the value group of F, which of those balls does A live in? And the point is, each one of those balls already contains an element of this field, namely the center of it, X. Right? So if X is an element in F, and gamma is in VK, then already X is in this ball, completely trivially. So every one of those balls is already witnessed, if you like, by an element of this field. And so in model theoretical terms, what this is saying is that this single extension generated by A here is this subfield, this sub-value field is existentially closed. Every existential formula, or every existential formula using parameters from this subfield, which has a witness A, already has a witness down here. Another way of putting that is some L-val quantifier-free formula with extra parameters from down here, which is true at A, is already true at some element of this field. And essentially that's exactly the claim, that this linear type determines the isomorphism type. So this symbol, this existential closure symbol, I can just write down a little bit more cleanly now, just as an aside. So this means, for a structure, pair of structures M and N, that for all A bar in M, and for all A bar in M, and for all quantifier free formulas phi, if n already believes that there exists y bar by a bar y bar, then m already believes that. Okay? So if there are witnesses, if there are points, if you like, upstairs, then there should be points downstairs. That's what existential closure is about. Okay. So putting all of this together, we get, and I'm putting all of this together, we get an existential closure from this thing to k, and that's how we extend this map. Essentially, every quantifier free statement here is already true here, so we can put it over here by this embedding, and so we can all infinitely many of these statements, just all the true statements about k are sort of true in some sufficiently saturated version of L. Like that. Okay. So that's a little sketch of one argument for this embedding principle that underlies Robinson's theorem. Okay. So, where do we go from here? Let me give a general statement of AKE principles. As a kind of general property, what might be true? What kind of statement are we going for? So a class C of valued fields, maybe with extra structure, but we don't have to think of that, is an AKE class I'm going to leave a little space here. If for all KVLW in the class, we have KV elementarily equivalent to LW if and only if, but actually I want to make it more general than that. So I immediately want to think a little bit more broadly than just elementary equivalence. So let me just stick a stupid, arbitrary, abstract box symbol here. But I want box. I want you to think of any of the following symbols. Elementary equivalence. I'm going to give you an if and only if, right? Elementary equivalence, equivalence of existential theories, that means every existential statement true on one side is true on the other and vice versa. Elementary substructure, and this existentially closed thing I just described to you. So I'm giving you kind of 4 AKE principles in one as a kind of definition. Okay. Now, what should it be if and only if? Well, now I need to add one more ingredient for this to make sense. It's not going to be meaningful for us to have an AKE principle around these two relations, these two binary relations, if the two structures that we're given are not already in some kind of relationship to each other. So in the case where box should be this thing, then we are already given an inclusion between them. Okay. So this is what I mean by an AKE principle is one of these 4 statements about a class of valued fields. Now there's a boring observation, which is that we've already seen AKE equivalence for the class of ACVFs of equal characteristic. That's what I was just telling you, but it's a really boring statement now. Because now it says, well, they're elementarily equivalent if and only, two such are elementarily equivalent if and only if their residue fields are elementarily equivalent, but we already know there's only one theory of algebraically closed fields of characteristic P, fixed P, remember, and there's only one, and their value groups are elementarily equivalent, but I already said there's only one theory of non-trivial divisible ordered abelian groups. So what this amounts to is just a boring version of the next Kochen Ershov principle. Another observation, AKE elementary equivalence is false for all ACVFs. Meaning for the class of all ACVFs. Because it's true for the class of some, a class of some. So why is that? Can anyone see that? Quickly.
What is the characteristic?
It doesn't, right, it doesn't tell us enough about the characteristic of the field. So we might seek to adapt AK principles by adding in extra bits of information. We could say an AKE plus characteristic principle is where, you know, blah box blah, if and only if blah 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 blah, and the characteristics agree. So we could augment this family of properties, if we like, and we will later. Okay, and the goal then of the rest of today's lecture, or principal goal, I'll say a few other things as well, is that the class of henselian valued fields of equal characteristic 0 is an AKE class for all four boxes. Okay, for all four of these interpretations here. Okay. Any questions at the moment? We're going to do some wiping. So yeah, now's a good time for questions.
The tensor product is especially embedded.
Yeah, so that's the technology of Kaplansky, which I will get into more detail on in just a second. I mean, that's a totally valid question, which I'm sort of going to get towards. Is anyone still writing this part? Okay. Okay, so what I want to do now is introduce a little bit more structure so that these arguments I skimmed over here become clearer and we can put a bit more flesh on the bones. The first bit of technology is to introduce precise versions of these lifts of the residue field and lifts of the value group that I used. Right, so I said let's take a maximal trivially valued subfield and so on, blah 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 blah. So what's that all about? Well, so definition. So given a valued field, I'm just going to say it's equal characteristic for now. Just think about equal characteristic. A section of the residue map, I'll just say section, is a function S from the residue field to the field itself, which is a, what do I want to say, right inverse of residue. And that's a section. You could also think about partial sections. And just some very brief observations. In residue characteristic 0, sections always exist.
Don't they just always exist? Or you didn't impose any assumption about being a homomorphism? Or do you want it to be a homomorphism?
Yeah, you're quite right, thank you. It's a morphism, yes. It's a ring morphism. Thank you. It's a ring morphism. And now I need to be just a little bit careful about lifting p-bases and things in positive characteristic. But in characteristic 0, you can lift a transcendence base arbitrarily and then use Hensel's lemma for the rest. So that's lift a transcendence base arbitrarily, meaning to arbitrary lifts of that residue class, and Hensel's lemma for the rest, henselianity for the rest.
So you need to compute a zero.
For the rest. You're quite right, thank you. Observation of residue characteristic, henselian. Thank you. Absolutely, thank you. I see I meant to give the definition only for henselian things. Okay, thank you. In fact, more general fact, if you don't mind passing to an elementary extension, sections always exist. And just to be clear, I'm talking about setting of henselian plus equal characteristic. Okay, so henselian valued field of equal characteristic, as long as you don't mind a little bit of going to an elementary extension, you can always find a section. So that's something about the residue map. That's somehow about finding copies of the residue field inside the main field. What about the value group? Definition, a cross-section is a group homomorphism which is right inverse to the valuation itself. Again, you could talk about partial ones, and again, observation. For KV henselian and sufficiently saturated, which is model theory speak for if I don't mind going to an elementary extension. Okay. We always get cross sections. It's the same idea, which is to say, if you want to argue that something exists after passing to an elementary extension, by the compactness theorem, what that really amounts to is saying every finite piece I can already find somewhere. I can lift any finitely generated subgroup via a homomorphism, which would then be a partial right inverse. And how do I do that? Well, a finitely generated ordered abelian group, as a group anyway, is just a bunch of z's. So it's got some generators. We can just lift those generators freely. Okay. If you have a section, you get one of these things, angular component. So what on earth is that? Well, that's something a little weaker than a section. An angular component, I'll call it AC, excuse me, and it's a function from big K times to the residue field times that is multiplicative and it extends the residue map. At least on the units of the valuation room. Right, strictly speaking, 0 is not in here, so okay. Well, and nor's the mag. Yeah, as you like. Sorry, extends the residue. Okay, extends the residue map on O times. Yeah, that's what I wanted to say. Sorry, we must ignore the whole maximum ideal for that part of the statement. Now, what have these three things got to do with each other? Well, I think of this one as quite separate. That's about lifting the residue field. These two have something to do with each other. Namely, to find angular components, the easiest way is to find a cross-section. A cross-section is always much too strong a thing, makes life very, very ugly. But an angular component is very nice to get your hands on. It's asking for, informally, it's asking for the leading coefficient. So in QP, for example, you could get, if you had a sum like this, and suppose I've written it like that, where a little n is not 0 and a big N is not 0. You know, the AIs are the standard digits. You know. Excuse me. Well, I really mean the Teichmuller limits, but never mind. The angular component then should be the leading coefficient, which is the A little n. Well, that's the idea. Now, why do we want these things? Well, these things are about the following. If I can point back at these pictures here, we want to know firstly that these types of things exist, these big subfields on which the valuation becomes incredibly simple. Either trivial, or somehow nothing to do with residue and purely just a copy of the multiplicative group getting stuck on. Right? And if we know that there is a section, then we get this. If we know there's a cross-section, we get this. So these two things are very much section, cross-section. Okay, this would be the field, the subfield generated by a section, and the subfield generated by the image of cross-section. Moreover, an exercise.
The example we gave with the QP, is the value supposed to be A, the residue of AN, or is not AN itself?
Sorry, thank you. Yeah, the residue. Thank you. Yes, you're quite right. The residue. Thank you. Thank you. All right, so a little exercise. If we let L be co-prime to the residue characteristic in some Henselian valued field KV. and we take any, with an angular component map, and let A be some element of the multiplicative group, then A has an Lth root if and only if the value of A is divisible by L in the value group, and the angular component of A has an Lth root in the residue field. How can I write that? KV times L. Okay. This is quite a powerful statement. It's saying that as long as you're just talking about radical extensions that have nothing to do with the residue characteristic, knowing the value, knowing sort of divisibility properties of the value of the valuation in the value group, and knowing the angular component already tell you everything. Okay. So that's quite a powerful tool. Okay. So now I want to add in a little bit more Kaplansky theory, and then we'll be ready to give a rather quick proof of AKU and residue characteristic 0. Again, now's a great time for questions.
Yeah, I guess I'm not sure. The observation you made for cross sections is true in positive characteristics as well?
Which observation? This last thing?
The one about cross sections. It's true in
This thing, this one here?
Yeah.
Yeah, it is, yeah. I mean, it's the same game, right? To embed, to find a cross section, it suffices to, by compactness, to find a lot of partial cross sections. Right? And what are they? They're just finite, they're just partial cross sections with domain of finitely generated ordered abelian group. Right? So just lift some generators arbitrarily. That's the kind of compactness way. P doesn't really come into it because not being able to take P roots is a problem if you're trying to extend a particular partial cross-section on a particular field. But if you don't mind twisting things, then you can always find enough P roots lying around. Okay, so final ingredient. This is a bit more of this Kaplansky theory. Okay. So, setting now. We've got a value field, and X an element of some valued field L extending big KV. Okay? And I want to work under the hypothesis that KXV over KV is immediate, which I already said means that the value group and residue field don't change. And we want to describe, or we want to show, that suitable assumptions which will certainly be valid in the case of Henselian valued fields of equal characteristic 0, that the isomorphism type of KXV V over K is determined by that linear type. Okay. So, linear type over K. So this was, if you recall, this is the list of balls over K, meaning center in K and radius in the value group of K, containing the list of those balls containing X. Okay, that's all it is, and it's like that kind of infinitesimal ball, if you like. Okay. So for a function, or it's going to be a polynomial. So for a polynomial f over k, we can write that f of y squiggle arrow tends to, in this slightly adapted sense, sum A to mean, and I mean now as y squiggle arrow x, right, to mean, so the value of f of y tends to sum A as y tends to sum x, to mean that in some ball of radius gamma containing x, or f, y, or let's say f is of constant value. Right, so I'm a constant value A. Right. So I'll write the value of f goes to some A as y goes to this x, to mean that there is some real ball, some ball defined over the field that we're working over which we're working. So that on that ball it has a constant value. So you can just say sort of, it is eventually constant. The value is eventually constant, or the polynomial. Okay, and the point is, point will be that in the residue characteristic 0, every polynomial without a root, without I'll say it more precisely in a second. Every polynomial's value is eventually constant. So how does the fancy get into this? You start with f and you write down formal Taylor expansion in a new variable. So for any polynomial f, we have such an expansion defined over the subring generated by the coefficients of k. I mean, this is a sort of Z algebra thing. This is happening sort of uniformly over Z, so that such an expression makes sense. For some choice of fi that is determined polynomially in the coefficients of f, we will always have this expression. Okay? It's a kind of ring scheme thing. So how do you calculate? What has this got to do with? What has this got to do with calculating the value of anything? Well,
Do we take this expansion from 0 to infinity?
thank you. I just mean it's just a finite expansion. This is just a polynomial algebra. So it's a formal Taylor expansion, but in the polynomial sense. That's all it is. So the FIs are just some polynomials playing the role of these derivatives.
So you want to assume that small x is not in K?
Not yet, but that's when we're going to apply it. When small x is in K, then none of this will be very relevant because then all the balls around X defined over K will already just tend to that one point. I mean, there's exactly one point in K itself. Also, the polynomial variable x equals little x is a polynomial then over K, so that's not great. Okay, so remember that when two summands have differing values, when some A and B have different values, the value of A plus B is the minimum. So that tells us that the value of, we want to calculate, say, how the value of f of y, when we plug some little y in, relates to the value of f of x when we plug a different little x in. And we want to eventually say, we want to sort of eventually plug our little x in here and let this one sort of vary through elements of k. And we want to argue that somehow this must always equal, the value of this must always equal this as long as this thing is sufficiently big. So let's look into this. What is the value of one of these things? Let's just plug an x in here. That's just something like this. So if you have a y that's gamma distance from x, right, this monomial's value is then somehow just linear with gradient I. Okay, so thinking of f as thinking of little x as fixed, that tells us that the value of this monomial is linear in the distance, if you like. Okay, and the gradient is I, and all these i's are different. Now, that should instinctively that should tell you something, right? You've got a bunch of straight lines with differing gradients. You should worry about 0. Maybe there's some sort of cancellation. But actually, no. There's nothing bad with characteristic P coming into this part of the argument. So this part works entirely uniformly. Eventually, what this tells us is that eventually, as you take your gamma larger and larger and larger, you must get to a point where there is a unique minimum value. So for some gamma 0, if the value of y minus x is bigger than gamma 0, then the value of the sum on the right-hand side is equal to the minimum of the values of these monomials. There is a unique one, and this value is equal to it, plus I. then it's gamma. Okay, so that's telling us that the value is eventually, the value of the right-hand side is eventually linear. Eventually linear and increasing unless I is 0. Okay, let's think about that. So if it's increasing, what does that tell us? If these, bear in mind that the x we want to think of as fixed. So if f of y is different to f of x, then this thing will always be the minimum of the value of the left-hand side and the right-hand side will be the minimum of those two. So that's telling us that for sufficiently great gamma, bigger than whatever gamma 0 that you needed there, we get that the value of f of y is equal to the value of f of x whenever the value of y minus x is greater than, or well, is gamma, let's say. Okay. So this is the kind of generic behavior we'd like to see. There is a problem. This is only going to be true in the case that all of these things have values. And that might not be the case if I is the power of p. And if we've got this problem coming from the characteristic, then we're in trouble. And this is not going to be true for all for all combinations of x and k in that setting. I see I'm wildly over time now. Okay, I didn't quite get to finish this argument today. I guess I'll have to pick it up on Thursday. But if I can leave you with the thought that at least when there's no prime p around, this argument tells you that the value of any polynomial at your element x is already determined in some ball around x with real points, with points already in the smaller field. I'll leave it there for today.